Welcome to another lecture within a course on optimal and robust control given at CTU in Prague. The focus of this lecture is on constraint optimization, and in particular we are going to develop first-order necessary conditions of optimality using the technique of Lagrange multipliers. So the motivation for us is to solve the following problem. We are given a function f of x and we are going to find its minimum. X belongs to n-dimensional Euclidean space, but unlike in the previous lectures, this time we cannot choose just any vector from the n-dimensional Euclidean space, but rather we need to follow the constraints that are generally written like this. Generally we have m constraints which come in the form of nonlinear equations. So this is our problem statement. And the goal for this lecture is to develop necessary conditions of optimality. Let's now start with an example. We will consider optimization of a linear function of two real variables, and the function will look like this. And so x, the vector x, is apparently coming from the Euclidean plane. And now the constraints will come in the form of a quadratic equation, namely it will look like this: 1/2 of x transposed times 1, 1, 1, 2 times x plus 0, 1 times x minus 1 is equal to 0. So this is the function that we are going to analyze. First, let's have a look at the cost function. And apparently it's a linear function, so no surprise that its contour plot looks like this. That means that the function grows towards the warmer colors, towards the orange and red color. Now, so this is the contour plot for cost function. And now how does the set of all admissible, acceptable or feasible solutions look like? Well, again, no surprise that it's just an ellipsoid. So unlike in the unconstrained case, here we can only think about those x that lie on this ellipsoid or ellipse. Now if we put these two sets or these two graphs together, looking at the resulting graph, we can immediately, without any theory, we can immediately argue what is the minimizer here. Clearly it will be somewhere around what some say, so my guess, I will put it here, my guess is that x will be something like 1 1/2. This is my guess. Sorry. Now, how can I, or what was the clue? What made me think that the minimum is in the identified point? Say, I will here display directly the solution. So even from this graph, it's clear. The graph that shows the accurate solution, it shows that I was nearly accurate. So what was the intuition behind it? I think you follow the same reasoning here, and that is that that the contours of f of x were collinear with with the tangent. With the tangent to the feasible set. That means tangent to the set which satisfies the following equation. Right, this is what guided me. Now I can rewrite this equivalently into saying that gradient of f is collinear to the gradient of h. I can write it like this. Gradient of f of x is equal to some constant times gradient of h. Now if I combine this condition with the original constraint, I obtain full necessary conditions, in fact first order necessary conditions, since I have the gradients there, necessary conditions of optimality. And indeed this provides the full solution of the problem of this particular simple problem. But let me now show you yet another way how to arrive at this particular solution. And this consists in introducing a new auxiliary function which we will label as L, and the function will be obtained in this way. It will be composed of the original cost function, optimization criterion, plus some coefficient times the function that defines the constraints. Now this new coefficient over here, or new variable, is called Lagrange multiplier. And the new function, the auxiliary function, also called Lagrangian function, is a function of two variables, x and lambda. Of course, in our case, I still need to keep in mind that x is actually a vector, whereas lambda in this case is just a real number. Now, using this new function, I can rewrite these necessary conditions in the following very simple and compact way, and that is that Lagrangian of L is equal to 0. Now, if you cannot see that these two conditions, or perhaps I will put it now like this. If you now cannot see that these two formats of the conditions are identical, just recall that Lagrangian function is a function of both x and lambda. Therefore, I can rewrite this condition as Lagrangian of L with respect to x, which is what did I say? So gradient of Lagrangian with respect to x is equal to gradient of f plus lambda times gradient of h is equal to 0, and then gradient of L with respect to lambda is equal to just h of x is equal to 0. And now comparing the two, I can see that these are indeed equivalent. Well, perhaps what might bother you is that up here I have plus, but it's just a matter of convention. I can immediately, no problem at all, relabel these coefficients, this coefficient lambda with its negative value, and I obtain identical result as the one derived from Lagrange function. Fine, now let's now count the number of equations and number of variables. So I have x1, x2 and lambda. That means 3 variables. And I have 3 equations. Right? Over here I have just one, but this one contains actually 2 equations because it's just one vector equation. Remember that the gradient of f actually is composed of 2 components. So that's it. That's essentially it. That's the key trick that we will use for solving constraint optimization problems. Let me now extend this without any proof. Let me now extend this to the general n-dimensional case and for general m constraints. So the procedure will be that I will simply form Lagrangian function, which is a function of the original vector x, and this time a vector of Lagrange multipliers. So I can either write it using the summation symbol as this, or I can use the compact matrix vector notation and write it like this. Now f is a scalar, of course. Lambda transposed is as a row vector, and hi is a column vector, so things are compatible here, and the Lagrangian function is a scalar function. So things look pretty neat and straightforward, and indeed they are, with some possible caveat here. In order to explain where the possible troubles lie, I would like to invoke yet another formulation of the necessary conditions, that means the definitions for the critical or stationary point. And this will be somehow just a reformulation or recombination of what we had for this particular example. So we said that either the contour lines are collinear or gradients are collinear, or by combining these two we can argue that at the critical point the gradient of the optimization criterion, now in this figure given by the red line or red line segment, so that the gradient of the cost function is orthogonal to the tangent line to the feasibility set, to the set of feasible solutions. Indeed, this is very useful interpretation of the condition of optimality, and we will elaborate on this further. But in order to see what kind of complications can appear here, I will consider another example, and this time in 3D. So my optimization criterion will look like, it will again be a linear function, so let's say it will look like 2 times x1 plus 2 times x2 minus x3. If you like, you can rewrite it directly in the vector format as 2, 2 minus 1 times x. And the constraints, so x comes from a 3-dimensional vector space. And the constraints, or I will put it like this. Now the constraints are given in the form of a single quadratic equation like this, minus x1 minus 1 squared minus x1 x2 minus x2 minus x1 squared plus 30 minus x3 is equal to 0. So this will be our problem. Since this is even more difficult to visualize than the previous case, I will again use Mathematica to show you first the set of feasible solutions. It's this particular quadratic surface, and please make sure that you really understand that this is just the set of feasible solutions. It's only those x that lie on this surface that we can use in the optimization, nothing else. And now I'm sorry that I always use the default setting for the x's, so rather than x1, x2, x3 in my mathematical plots, I will always have x, y and z. I hope you could live with it. Now, how do we translate the observation about the necessary conditions, about the geometrical interpretation of necessary conditions in this setting? If you form Lagrangian and find its gradient and set it equal to 0, you will learn that the critical point here is, have a look at how Mathematica does it for me. So the critical point is at the point 0, 0, 28 and minus 1. Should you be interested in the value of lambda? I'm not, so I will only put down x star is equal to 0, 0, 20, 28. So this is the critical point. And here it is. Can you see the blue dot over here? So this is the critical point for our optimization problem. Now invoking the interpretation with the gradient of the cost function being orthogonal to the tangent space, tangent plane, I obtain this figure over here. So this plane over here is tangent plane to the critical point, and the arrow behind the surface is actually the gradient of the cost function. So we can see that indeed the characterization of the stationary point that I gave is satisfied here. By the way, just in case we need it, the gradient of f at the critical point is 2, 2 minus 1. So I'll put it here. All right, so apparently the crucial role here is played by the concept of the tangent space. So we need to elaborate on this further, and the criterion that I have only pronounced in words, I would like to make it more formal and rigorous. In order to do such rigorous analysis, we need to do something similar that we did in the unconstrained case, and that is that we analyzed how the function evolves if we perturbed the independent variable along some line. Here in this case I cannot perturb it over the line because the line here does not belong to the feasibility set, so I only can analyze it, I only can study the function as it evolves over the surface, along some curve over the surface. Let me now try to sketch this here. So this 3D drawing can be pretty tricky, but I hope I will manage it. So x1, x2 and x3. Now my feasible set looked something like this. So this was my feasible set, and then somewhere over here I have the critical point x star, and say this is the tangent plane to the critical point. Now what I want to do is I want to create a curve that goes over the surface, and I will label all the points on this curve as x of alpha. So the points will be parameterized by a real variable alpha. Now, all right, so let's write this down. So I will consider a curve parameterized by a real variable alpha, and moreover x at 0 goes through the critical point. Fine. Now, in the same style, as along the same line of reasoning that I applied in the unconstrained case, I will now calculate the derivative of f when evaluated over this curve. That means derivative of f of x of alpha with respect to alpha. I will again invoke the chain rule for differentiation, and I will obtain gradient of f at f of x of alpha. Now, since this is a column vector, I need to transpose it and multiply it by the derivative of the argument, which is derivative of x with respect to alpha. Now, if I evaluate this at alpha equal to 0, this is what I obtain, and I can rewrite it as let's do it in this way. So gradient of f at the critical or stationary point times x prime at 0. So what do I have here? Here I can see that the gradient of the cost function at the critical point is orthogonal to this vector. But what is the interpretation of the vector? You can see the interpretation clearly after expressing the first few terms in Taylor's expansion of x alpha. So the first term is actually our stationary point plus x prime at 0 times alpha plus some higher order terms. So now you can clearly see what the interpretation of x prime 0 is, and the interpretation is that this is a vector that is tangent to the set of admissible or feasible solutions at x star. In other words, this vector lives in the tangent space to our solution set at the stationary point. So this is first important observation. But we will see that something similar can be learned if we now investigate the constraints. So the constraints, when analyzed along x alpha, so I will have m of these. And now if I differentiate them with respect to alpha, what I obtain is again using the chain rule. So what I obtain is d with respect to d alpha of h of x of alpha. So again, gradient h1. So gradient of h1 of x of alpha times x alpha. Once again, I hope that this is clear, that this guy over here is a row vector, this guy over here is a column vector. And I can proceed for all other terms as well. Derivative of h2 of x of alpha with respect to alpha is equal to gradient of h2 of x of alpha transpose times x alpha, and so on. Now, if I evaluate these at alpha equal to 0, what I get is d of h1 at x prime with respect to alpha evaluated at alpha 0 is equal to gradient of h1 x prime transposed times x prime 0. Of course, I had a typo in the previous derivation here. I should also have x prime. This was derivative of the inner argument. And similarly for all other terms, so up to dh2 with respect to d alpha evaluated at alpha equal to 0 is gradient of hm at x prime times x prime 0. And now I see I should have left some space, so I will do it like this. So all these derived terms should be actually equal to 0, and in fact I can also correct it over here. So this should be equal to 0, this should be equal to 0. Fine. So let's summarize what we have just learned. We have learned that it's not only that the gradient of the cost function should be orthogonal to a vector from the tangent space, but also the gradients of the constraint functions should be orthogonal to the tangent to the feasibility set. Fine, this sounds interesting, but now can we also turn it upside down? Can we also make the following argument that if I consider a gradient of hi at the stationary point, Now, if I find some vector d that is orthogonal to all the gradients of h, like 1, 2, up to m, can I infer from this, or can I conclude from this, that d belongs to the tangent space to the feasibility set? And the answer to this question, in fact, it's a pretty important question. In fact, we are asking, through this question, we are asking what is actually the characterization of the tangent set? Is it enough to characterize it by requiring that it's all those vectors that are orthogonal to a set of vectors, namely the gradients of h, so m vectors? And the answer is, well, is yes, sort of. Well, yes, if x is a regular point. Now, what does regular point mean? Regular point means that the gradients of the individual constraint functions evaluated at the stationary point are linearly independent. So if this is the case, then yes, then we know how to characterize the tangent space. Let me show you an example. In this case, in this example, the constraints will be linear. These will be given by a set of linear equations written in the matrix vector form as A times x is equal to b. Now, A is a matrix with m rows and n columns. Therefore, x belongs to n-dimensional vector space. Now, this can be rewritten into A times x minus b is equal to 0, and this gives us clearly m scalar linear inequalities h1, h2 up to hm. Now, the condition that the gradients should be linearly independent can be written like this. That vector that I will compose of the, or actually matrix composed of column vectors, gradient of h1, gradient of h2 up to gradient of hm. This matrix I will label as gradient of h. In fact, this is no longer a vector, so it's kind of abuse of terminology here. This is very often called in literature as the so-called Jacobian. It's a matrix, Jacobian matrix. And now this Jacobian matrix can be computed in our case as just A transposed. So if the columns of A transposed should be independent, that means the rows of the original A matrix must be linear independent, and that means that the conditions define a the conditions define a regular point if and only if the matrix A is full row rank. In this case, the set of constraints is non-degenerate and it defines a regular point. All right, so now we know the fundamental restrictions here. And if these conditions are satisfied, then we can write down finally the first order necessary conditions. So we assume that X is regular, and then the condition of the necessary condition for optimality is that the gradient of f evaluated at the stationary point, regular stationary point, times d times some vector d is a zero, in the words that it's orthogonal to such vector d, or all those vectors d that that are orthogonal to the gradients of the cost functions. Let me write it down as gradient of h I at x star transposed times d is equal to 0 for I is 1 to m. So this is one way how we can express the first order necessary conditions of optimality, but clearly this is equivalent to saying that the gradient of f at x star is in the span of the gradients of the constraint functions. Well, this is just a compact way of saying that actually you can always express your vector, I mean, the statement that a certain vector lies in the span of some set of other vectors. This is just a compact way of saying that you can express your vector as a sum of linear, or as a linear combination of those vectors. So let's say lambda 1 times gradient h1 plus lambda 2 times gradient h2 and so on. And finally you can rewrite this in the already familiar way, again after relabeling these constants. There's nothing wrong about it. We do not change the meaning of this expression, whether 3 or -3 in this case doesn't matter. Or actually, sorry, forget the latest comment. The truth is that the truth is here that I can label my constants as I wish, which will allow me to write it down like this. And this is the already advertised first order necessary condition of optimality, right? For completeness, I will also rewrite it as using the Lagrange function, so f plus lambda transposed times h, and then using this definition, this is just equivalent to saying that gradient of L is equal to 0. Fine, so now we formally, not really proved, but went relatively deep into the derivation of Lagrange multiplier procedure. Let me now show you a few examples, or show you what could go wrong if the conditions are not regular. So the first example will be in R3, and well, in fact, no, the plan was slightly different. Before showing you these degenerate situations, I first wanted to show you actually a nice situation in which things go fine, and the situation is over here. So I will have on top of the example that I had before, I add another constraint. So besides the original constraint, I will have another nonlinear constraint. So clearly, these are the two surfaces. Maybe here it's somewhat better. So clearly, the set of feasible set, the set of acceptable vectors here lies at the intersection of these two surfaces. This is the set over which I can do the subsequent optimization. Now, what do the conditions that I derived, what do they tell us? I mean, in particular, that geometric interpretation that the gradient of the cost function must lie in the space generated by the gradients of the two cost functions. Now, let's say if I investigate the function in the point somewhere over here. Now, the gradient of the constraint function corresponding to the orange surface is a vector that points out of the surface, right? It's normal to the surface. Similarly, for the blue surface, again, the gradient points out of it. It's a vector that is normal to the surface. So at the particular point, the condition of optimality for these non-generate surfaces tell me that the gradient of the cost function should lie in the plane that is orthogonal to the tangent line that is tangent to the feasibility set. That means this intersection of the two surfaces. Sounds pretty complicated, right? The great advantage of the video is that you can rewind it and listen to it a couple of times. So now it's time to show you actually where things can go wrong. The example will look like this. So first equation will look like this: x1 minus x3 squared is equal to 0, and the other constraint will look like minus x1 minus x3 squared is equal to 0. Now let's have a look at how the two surfaces look like. It's the blue. The blue surface corresponds to one constraint, the orange one corresponds to the other constraint. Clearly, they have a non-zero intersection, similarly as before. In this case, it's the x2 axis. So the set of feasible solutions lies along the x2 axis. And now let's have a look, even visually without computing anything, let's have a look at what does the at any point, pick an arbitrary point along the x2 axis, say the origin of the coordinate system 0, 0, and what are the gradient vectors to the two surfaces. Obviously, they point along the x1 axis, right? The two are collinear. So now the space that is spent by the two, or spent by these two vectors, is just a single one-directional set. So now the condition that your gradient should lie in this set seems overly restrictive. And this is why the Lagrange technique fails in this particular example. Let me show you yet another example that in fact we can have non-regular point even in the situation with just a single constraint. Say this single constraint will be just x1 is equal to 0. Now this means that the feasible set looks like what? It looks like this is x1, x2. So it's the whole x2 axis, right? Now the gradient of h is equal to 1, 0, constant everywhere, so certainly also on the x2 axis. And now let's recall that the condition of linear independence can be actually also applied even to a single element set, in which case it means that the vector is non-zero. And in this case, yes, the gradient, this single vector, is non-zero, so we can regard a set generated by the single vector as linearly independent, and it does comply with the definition of a regular point. Now let's have a look at how things change dramatically if I redefine the feasible set as the set of all those x1 and x2 that satisfy the following equation. x1 squared is equal to 0. Obviously, although this is a different function, the resulting set is identical as before. It's just the image is just the x2 axis. But this time, how does the gradient of h looks like? The gradient of x in general, the gradient of h in general is 2 times x1 and 0, and when evaluated at the vector 0 and x2, any x2, it's equal to 0. That means it vanishes. The gradient vanishes here, and we have a non-regular point. And again, the Lagrange approach will fail here. What's the message here, or the lesson learned from these two examples? In particular, the second one. Very often, if we encounter some non-regularity, very often it's just a matter of not quite clever formulation of the problem. Very often you can go back and you can perhaps define your optimization problems in a better way so that this non-regularity is removed. Fine, now let's discuss the last two issues, and that is, perhaps you may have the impression from what we did so far that we just converted the constrained minimization into unconstrained minimization. but it's not exactly true. So in particular, what I want to emphasize is that local optimum of f is not necessary a local optimum of Lagrangian function. Strictly speaking, what we are after when working with the Lagrange function is just the critical point or stationary point. We are not really trying to minimize the Lagrange function. We only want to find its critical point. Let's consider the following example. So let's now maximize x1, x2, x1 times x2, subject to the constraint that x1 plus x2 minus 2 is equal to 0. Now I'll leave it up to you to form the Lagrangian and find the first order necessary conditions and see that the constraint problem does have a maximum. We will only discuss the second order sufficient conditions of optimality for the constraint problems in the next lecture, but this time you can just have a look at how this looks like in a graph. So this is it. So over here you can see the original cost function for the unconstrained problem and then its restriction due to the linear constraint. The critical point is highlighted here using the red point just over here. So just inspecting the graph we can conclude that yes, at the particular critical point, which is as you can read somewhere over here, yeah, it's 1, 1 minus 1. So the critical point is this, and at this particular critical point the original cost function is maximized. Fine, but is it also true that the Lagrangian function is maximized? Now you are already equipped with the tools to check if it is the case or not. For instance, you can compute the Hessian of L. So yeah, do it please. So calculate the Hessian of L as a function of x and lambda and tell me your conclusion. The answer is that no Lagrangian function in this case is not maximized. On the other hand, what if we turn it upside down? So what if what we find is indeed a local minimum of L? Then yes, then if your x and lambda they minimize the Lagrange function, then they do also minimize the original cost function. How can we see this? Just let's now have a look, one last look in this lecture at the Lagrange function. So it's the original cost function plus lambda times h of x. And now say you found a certain combination of x and lambda for which the value of L is minimized. But as long as the x that you found is satisfying the the constraints, if it satisfies the constraints, then you can actually disregard this term over here, and the value of the function of the L function coincides with the value of the original cost function, and it cannot be made smaller because the term that stands by the lambda variable is a 0. And that's essentially it. In the next lecture, we are going to investigate the sufficient conditions of optimality for the constraint problems.